Okay, today we're going to talk about chord and twist distributions and their impact on the wing. This should help you with the homework. In this current homework, you're going to be designing a wing and trying to come up with a good lift distribution, lift coefficient distribution, and we're going to talk about how you do that today. All right, so, sorry, it always takes a minute to share my screen with this. Okay, here we are. Part 2 in our discussion. First we got to ask ourselves the question, what kind of lift distribution do we want? In other words, what's an ideal lift distribution? Well, there of course is no one answer, it really depends, but one answer that we've already kind of talked about, remember when we talked about induced drag, what was the lift distribution that minimized my induced drag? It gave me the smallest induced drag. Remember, this occurred when that term E implicit was 1. If you recall, right, this is the back view of my wing, it was when the lift distribution looked like this. It was an ellipse. We had an elliptic lift distribution. Okay, so this is elliptic. Meaning if I was to plot those forces that were acting over the wing, they go to 0 at the wingtips, and right at the center, they kind of come up, and that shape, those forces, that distributed load, be an ellipse. That is the minimum induced drag solution for a fixed span and a planar geometry. Okay, so in many ways, like we talked about before, this is not exactly what we always want, but most airplanes are going to be pretty close to this. So this is a kind of a good guiding star, if you will, at least where to start. An elliptic lift distribution is desirable. So how do we get that? Well, one way is that we could make our wing shape an actual ellipse. So let's make the wing. Here's a top view of the wing now, right? And then the fuselage. And then we got some tails. We could make the wing elliptical. And the most famous example of that here is the Spitfire. So it had an elliptical wing shape for that reason. However, we don't usually see elliptical wings anymore. So an elliptical wing will produce an elliptic lift distribution if you give it no twist. The reason why we don't do this anymore is because if we twist the wing, we can actually create any lift distribution we want, right? You can give me any shape of the wing. It can be a rectangle, it could be trapezoidal, it could be some complex, whatever shape you want. We just change the twist until we get the lift distribution we want. So it's decoupled, right? The shape does not change or does not determine lift distribution. I can twist it. I mean, it certainly affects it. It affects the twist I'm going to get, which we'll see will then affect other things. So it's not like these are independent. But the point is, even though I said they're decoupled, well, let me back up here. The point is that no matter what geometry we give it, we can always get an elliptic lift distribution just by retwisting the wing the way that we want. Okay, so I guess in some sense you could say it is decoupled. Okay, so we can get any twist we want. So I can create a rectangle. I can create a tapered wing. I can create crazy shaped wings, whatever I want. I'm going to get an elliptic, or I can get an elliptic lift distribution if I want. All right, well, let's see what the implications of that are. So what I have on the left is a lift distribution. And this is common in a aircraft. Just show this. So here's like, say, half a wing. Y is always the span-wise coordinate. So there's really another half of the wing, but by convention, almost always, these aircraft are symmetric, and so we only just plot one half. So this is like half of an ellipse. So if you wanted to plot the whole lift distribution, right, it would keep going to form an ellipse, but we generally just show half because it's going to be symmetric. And so the Y is out the wingspan, so right here would be the wing tip. Okay, so I said for any shape, I can get an elliptic lift distribution. So there we go, we've got an elliptic lift distribution, and I did it with 3 different wings. One was rectangular, that's the top. The middle one is an elliptical, and the bottom one is just a regular tapered trapezoidal wing. Now what I want you to draw here is what does the lift coefficient distribution look like? Okay, and it's going to actually be different for each one. Okay. So I want you to take a minute and see if you can fill out those graphs. What does the lift coefficient distribution look like? You may have to go back to the definition, recall what that is. If I know the lift distribution, which I do, it's elliptic, and I know the shape, which I do, it's right there, I can determine the lift coefficient distribution. It's not going to be the same for each one. Okay, so take a minute, try and fill that out. While you're doing that, I'm going to change this title because title text is an awesome title, but I'm going to put something awesomer. Impact on the lift coefficient distribution. So go ahead, pause it and finish that up. Okay, so the way we figure this out, let's go back to the definition. What is lift coefficient? Remember, this is lowercase cl because we're doing it for each airfoil. So it's a 2D thing. We're just calculating the lift coefficient of every little airfoil along the wing. So lowercase cl is the lift, L prime, and that's the same as this little L. Maybe I should call this L prime to be more consistent with what we have been doing. It's the force per unit length, divided by the dynamic pressure and the chord. Okay, so L prime, that's elliptic. C, that's my chord distribution. That's going to be determined by the shape here. And the dynamic pressure is going to be constant. That doesn't change across the wingspan. We're going to use it uses the free stream wind speed, so that's a constant. So in the first case, well, in every case, this numerator is elliptic. And in this first case with a rectangle one, the chord is just a constant. It's constant chord all the way across. So my lift coefficient distribution is going to look like an ellipse. And I didn't draw that very elliptically, like an ellipse, right? Because I've got an ellipse divided by a constant number, it's just an ellipse. Okay, second case, I've got ellipse on top here, right? And then I've got an elliptical shape, elliptical chord distribution on the bottom. So I've got an ellipse over an ellipse. So my chord distribution now is going to be constant, right, along the wing, and, you know, dropping off to 0. Okay, so that's that case. Now what about this last case? Again, I've got elliptic in the numerator, and in the bottom, I've got a chord that starts out high, and as I go towards the tip, the chord shrinks. So it depends on how it shrinks, but it's going to look something like this. It may be relatively constant at first because the lift distribution is dropping, but the chord is also dropping. But a linear taper drops faster than the ellipse, so we tend to get kind of a rise here, and then eventually it's going to drop to 0 because the lift drops to 0. All of these should have ended at the same place here for wingtip, but let's just pretend that they did. Okay, so this is the important point here, is that even though twist was decoupled, I could use twist to get any lift distribution I want. The planform shape still matters because it's now going to affect my lift coefficient distribution. Okay, so I said I wanted elliptic, but different shapes are going to give me different lift coefficient distributions. That's now going to beg the question, what kind of lift coefficient distribution do I want? Okay, so before we can answer that, we're going to, I'm going to give you a simple explanation of what we'll call critical section theory. So here's going to be that same kind of plot. Here's y, so that's along the wing, right? So this is the root of the wing over here, tip of the wing over here. And I'm going to plot a lift coefficient distribution again, and I'm just going to draw some random, not really random, but just some kind of shape. Okay, that's the lift coefficient distribution. And what we want to do, what critical section theory is going to do, is going to help us know when our wing is going to stall and where it's going to stall. So every airfoil has a CL, lift coefficient, every airfoil along the wing, but every airfoil also has a CL max. And I'm going to draw that too. Let's just draw it right like this. Okay. And it could be a straight line. When you do it for your homework, it's going to be a straight line. It's going to be constant all the way across because you're going to use the same airfoil. But in general, we don't have to have the same airfoil all the way across the wing, so it could be a curve like we see here. Okay, so what critical section theory tells us, remember, let me draw this plot here. Here's here's an airfoil, angle of attack, CL, and the curve is going to look something like this, right? So CL max is this point here, right? That's CL max. That doesn't change with angle of attack, so that thing is a constant. But what happens is, as I increase the angle of attack of my wing, right, then these CLs, this blue curve here is changing. As I increase CL, or angle of attack, sorry, I move up that curve. And so you could think of it this way. At a low angle of attack, you know, I'm going to have a CL that's maybe here. And then I increase the angle of attack of my wing, and it's going to move up and move up and move up. Okay? So increasing the angle of attack is going to move up this curve. And at some point, these two curves are going to touch. And critical section theory tells me that's when my wing is going to stall. So here's the important thing, takeaway here, right? These curves here on the right, that tells me my airfoil, when is the airfoil going to stall? But this is going to help me know when is my wing going to stall. And basically what critical section theory is saying is that my wing will stall when any one of these airfoils is going to stall. In other words, its CL reaches CL max, okay? This is an approximation. It's not exact because what this assumes, let me draw this wing here. So here's like the wing shape, okay? What this assumes is that the streamline over every part of the wing is, you know, perfectly parallel to the free stream. And so it acts like a bunch of 2D airfoils and they're independent, but that's not true. We get some span-wise components of the flow. So the flow across the wing actually has some curvature to it. We get these span-wise gradients that we may talk about later. So it's actually not true, especially for a swept wing, but it's pretty close. And even for swept wings, because of other reasons that we may talk about later, this actually works really well. Better than you might think. But the key takeaway here again is that to figure out when the wing is going to stall, we're just going to increase that angle of attack until the CL at any point in the wing hits the CL max. Or in other words, once any airfoil hits that point, any one of the airfoils on the wing, then we say the wing has stalled, okay? So with that background in mind, we can then better answer this question: what is an ideal lift coefficient distribution look like? We already said an ideal lift distribution is probably close to elliptic, but different shapes will give us different lift coefficient distributions. So what do we want? What's ideal? Well, if you think about it, if we go and look at this curve here, if this section of the wing has stalled, that means anything that is below the stall line is underperforming. We could have got more lift coefficient out of it, right? So in other words, if this blue curve looked like this, or in fact, if it looked like this, like it perfectly captured this line and every section stalled at the same time, that seems like it'd be more ideal, right? Because every section, we're getting the most out of every section. Because if any section stalls before another section did, then we could have gotten more out of that. We wasted it. So ideally, we actually want every section, this is actually not quite ideal, but let's go with it for the moment. Ideally, we want every section to stall at the same time. That means we got the most out of it, perfectly, the most efficient that we could get. And so because, in your case especially, but you know, let's in general, let's just say CL max is constant. Use the same airfoil across the wing. So that means we want a CL distribution that is constant across the wing. So as we increase that, and actually I'm going to draw it right at CL max. Let's just get rid of that for now. We want a CL that's going to be just constant. So that when we hit CL max or CL, or so that every section stalls basically at the same time. This is close to what we generally want. The problem with this is tip stall is something that we're quite concerned about. Okay, so imagine I've got this airplane. Here's the wing, and let's say that it stalls here at the tip first. If stall occurs at the tip, what's going to happen to my airplane? And think about that in contrast to where if the root had stalled, somewhere closer to the root. Well, if the tip had stalled, that means I had some lift here, and then suddenly it dropped significantly. It's gone away. I've got lift there and then it drops. Well, in an ideal world, let's say this tip and this tip stalled at exactly the same time, then I'd still be okay and I'd be balanced. But what's going to happen with tip stall is because of, any slight asymmetries in the flow, one's going to stall, at some different instant than the other. Now I've got this big imbalance. I've got a lot of lift on one side versus the other. My airplane is going to roll. I'm going to have a strong rolling moment. That's going to be really undesirable, right? That's not happy for the passengers. It's not happy for piloting. There's no people. It's not happy for an uninhabited aircraft either, because I need to control this. So I don't want tip stall. That's in contrast to if the lift was at the root, right? And then I get a stall, one of them drops off. Well, that's a much weaker rolling moment that's going to occur. That's not going to upset my balance very much. So I really don't want tip stall. That's something I have to be careful to avoid. This is actually why this type of lift distribution here would be particularly undesirable. Notice that it's going to want to stall right here, or else I'd have to really cripple my airfoils on the interior to get them to perform worse. So this is a particularly bad shape for me. So an ideal lift distribution actually may not be quite straight. We generally would actually probably prefer that it was pretty constant, and then towards the root it probably dropped a bit. Alternatively, we could use airfoils towards the tip with a higher CL max, but for your airplanes, you're probably not going to use different airfoils. And so in your case, you're going to want a lift coefficient distribution that's more like this, right? Where if it's the same airfoil, it's relatively constant inboard, and then it drops somewhat towards the tips. That's going to mean that stall is going to occur, somewhere inboard and not out by the tip. The other reason why we don't want it out by the tip is that that's where our ailerons are going to be. And ailerons are out there for the same reason, right? That the tip stall is bad, is because by deflecting ailerons way out here at the tip, I get a bigger leverage, so I don't have to deflect my ailerons as much to be able to get the turn that I want to. If they were too close inboard, I'd have to have big deflections to get the rolling moment I want, so I want to put them out. And if I'm stalling out where my ailerons are, then I don't have the control that I need. This is actually probably the worst problem than the tip stall, is that if I don't have ailerons, they're ineffective because I'm stalling, then I'm losing that roll control. So I want to make sure that my lift coefficient is dropping out there towards the tip where my ailerons are going to be. All right, so I'm going to show you this complicated figure, and it's going to take you a while to unpack this. So this is in the book. I'm going to have you refer you to look at it, but we're just going to kind of go through it pretty quickly, and you can go think about it more later. This figure is going to give you, or kind of explain some of these trade-offs again in the summary here. So first example, let's say I've got more or less an elliptic, or let's say, well, sorry, we're going to look at each of these separately. Chord, if I have a lower taper ratio, meaning I've got bigger chords at the root towards smaller chords at the tip, I'm going to get more lift inboard and less lift outboard, okay, because I've got the bigger chords. But the downside that I may have is that because these chords get really small, remember CL is going to be my lift. Sorry, I should be using L prime, but I've been using lowercase l here. Divided by Q divided by C. So because I have those smaller chords at the tip, then my lift distribution is going to jump up. This might give me, actually this kind of taper is better for my lift distribution because it's going to be closer to an elliptic. I want more load inboard and less outboard. Conversely, if I have a higher taper ratio, which means closer to a rectangle, I'm going to have a closer to a flatter lift. My CL curve might look a little better, but notice my lift curve, it doesn't look very good. This is not going to give me a good inviscid span efficiency. There's going to be more induced drag because it's not close to elliptic. So there's some obvious trade-offs with chord. Twist and sweep are not going to affect CL directly because that's affected by chord. But for twist, I can increase the twist inboard, decrease it towards the tip. This is called washout, where I decrease my twist at the tip. So this is pretty common. Wash in is the opposite, where I increase my twist at the root. So you can see what happens that if I have less twist at the tip, as you'd expect, I have less lift. If I have more twist at the root, I'm going to have more lift. So that's just, and of course the opposite with wash in. So wash out is used a lot because of this taper. If I taper here and I'm losing lift, then I may need to, or say it this other way, if I have too much lift here at the tip from these taper ratios, I can decrease my twist to kind of bring that lift down and increase lift above. So there's this complicated trade-off between chord and twist. You got to iterate a little bit to find something nice and workable. Sweep will kind of have a similar effect here, where if I sweep, if I sweep back, that's the normal way we usually see sweep. It actually loads up my tips, whereas if I swept forward, it kind of has the effect of washout. I lose lift at the tips. Okay, so you're gonna have to think about this a bit. I'm gonna come back to this in one sec to kind of to maybe try and consolidate these things, but I want to throw this in here before I forget. One other thing. This is somewhat of an aside, but I need to mention it somewhere. We talked a lot about how the lift curve slope for an airfoil is 2 pi. For a wing, there's not a universal number, and it's not 2 pi. It's going to be less, okay? Because every section, it would only be 2 pi if you had an infinite wing, right? You didn't have any of these losses at the tip and things, you know, from these, from the induced drag and the downwash. So it's going to be reduced. Reduced slope. That's important to keep in mind. There are some formulas in the book for ways to estimate this. It's going to be primarily a function of the aspect ratio. But the important point here is that you're going to get a reduced slope. Let's see. Let's see if I can add a page here. Yeah, let's just jump here to this page. Let's talk about how you can approach this in your homework. So there's kind of two things you're trying to do. You want an ideal lift distribution. And that means that it's going to be probably close to elliptic. It's going to be about elliptic. And you will know that because it's going to have an implicit span efficiency close to 1, maybe 0.99, maybe 0.98, but somewhere in that neighborhood, right? So you want to try to get something that's close to 1. You want an ideal lift coefficient distribution. And that's going to be, you know, maybe fairly flat and then dropping off towards the tip. It's not going to look exactly like that, but you want something, you at least want to avoid tip stall for sure. And you want to be efficient, meaning you don't have a lot of sections that are really underperforming. Okay, so but for sure you want to avoid tip stall, which means you want to avoid having your lift coefficient like jump up here towards the tip. Okay, so the primary knobs you're going to have to do this are the chord and the twist. Remember, the chord is going to affect both of these. It's going to change your lift distribution, right? If you have bigger chords at the root, it's going to increase the lift at the root. If you have, and everywhere, right? If bigger chords anywhere is going to increase the lift at that section. It's also going to affect your lift coefficient distribution, right? Because CL is lift QC. So chord is going to affect both of these. It's going to change the numerator, it's going to change the denominator. Twist is just going to change the lift distribution directly, but that's of course going to then indirectly affect the lift coefficient distribution. So these are going to be coupled. You're going to have to iterate and try these things a little bit. One more detail though that you need to keep in mind, and you know, you're going to have to think about this. I'll probably talk about this again in class a couple times. Or you know, on Slack when we talk about this. These two conditions do not occur at the same wing or airplane lift coefficient, or another way to say it, they don't occur at the same angle of attack. So in other words, you have, we'll call this CL cruise. This is going to be the lift coefficient that you normally fly at. This is your design CL. Okay, or you could think of it as your design angle of attack. That is the angle of attack that you want to be roughly elliptic. Okay, there's going to be another CL that you're going to look at. That is CL max. That's the maximum lift coefficient you can get to, because that's going to be at the point of stall. In that case, your this is lift, this is Y, and this is going to be Y, this is going to be CL. That's the one where you're going to care about having a relatively flat CL and then it's going to drop off. Okay, notice I drew this up higher. This is at a different angle of attack than the cruise one. In other words, this lift distribution here on the left is going to be something else over here. Let's say it looks more like this, whatever it looks like. We care less about the lift distribution at CL max. We care about our lift distribution the most here. We want to have low drag while we're cruising. If our drag is a bit higher at CL max, that's not as big of a deal. Similarly, because that's just there for the slowest speeds or right when we're approaching stall. Similarly, my CL distribution, this is my CL distribution. We care about it at CL max because that's right where I'm going to stall. It may look something different, right? Like maybe it looks more like this at cruise, but we don't care because I'm far away from stall. And we care about when this hits the CL max line. I'm going to draw it as red. And over here, this blue line, maybe it has even a shape that I don't like where the tip is high. That's okay because it's still far away from the line. What I just want to have happen is that once I get up to this angle of attack, that the tip is not stalling, if that makes sense. So to recap, there are two things I want to look at: ideal lift or elliptic lift distribution, a nice, efficient, non-tip stalling lift coefficient distribution. So those two things, but I look at them at different angles of attack. I look at the lift distribution at the angle of attack that I want to fly at. Most of the time I design CL. And I look at the stall one at the angle of attack at which my wing is going to stall when it's going to hit the CL max. Okay? So think about that. As questions come up, please ask me and we'll talk about that in more detail. I hope that gives you some guidance to get going though. Okay, have a good day. We're gonna, after you get your wings designed, we're gonna work on getting them cut on the foam cutter. So make sure to sign up for time to meet with the TAs at the foam cutter. We'll see you next time.